Hey, how are you? I'm the Amateur Logician from amateurlogician.com. I sincerely hope you are doing well. In this video, we're going to be exploring the logic of relations, of relationships. There's an underlying logic there that we're going to explore. Some relationships, for example, are reflexive, when we're thinking about how something can be related to itself. For example, every number is equal to itself. Some relationships are symmetric, others are asymmetrical, and some are anti-symmetric. Those are three different types of relationships, and we'll get into those presently. Being married to is a relationship that's symmetric, because if Tom is married to Alice, Alice is married to Tom. Some relationships are transitive, and equivalency is another very important type of relationship, which in fact combines the three previous relationships. Now, over a year ago on this YouTube channel, I produced a number of videos in the playlist called Basic Symbolic Logic Course. Within that playlist, you'll find videos on relational predicate logic. Presently, though, we're going to explore relations in a more general sense, at least when it comes to binary relations. Yet to start, I do want us to think a bit about predicate logic because it provides us a precise manner in which to think about these types of relations, but you don't need to know predicate logic in order to follow along. Now, when it comes to a reflexive relation, we can first think about this in terms of a diagram. Let's say we have X, and a reflexive relation is just thinking about itself. Think about equality. Equality is a reflexive relation. Or consider the example of having the same age as. That is likewise reflexive. And we could utilize the language of predicate logic to express that proposition. For all x, x has the same age as x. The upside down A represents for all or for every. X is the quantified variable, which can stand for anything whatsoever. For all x, x has the same age as itself. Now, being reflexive is in contrast with something that is irreflective. For example, think about being taller than. No one is taller than themselves. That's why it is not reflexive. We can likewise symbolize that into the language of predicate logic. So here we will say, it is not the case that there exists an x such that x is taller than x. The backwards looking E stands for there exists. Another type of relation that's possible is something that is symmetric. So consider the relationship between x and y. If x is related to y, and y is related to x in the same way, we have this loop between the two. Once again, consider the example of married to. That is symmetric. When a first thing is related to a second, and the second is related to the first in precisely the same way, we have a symmetric relation. And we can symbolize this as, for all x, for all y, here we have two things being related, x and y. So there are two quantified variables. So for all x, for all y, if x is married to y, then y is married to x. Notice that capital M stands for that relational predicate married to. So for all x, for all y, if x is married to y, then y is married to x. It's symmetric. Or consider sibling of. That's symmetric because if one person is a sibling of another, the reverse holds. Or consider trades with. If two people do a voluntary exchange, we have a symmetric relationship. In contrast, we have some relationships that are asymmetrical. For example, being a parent of is asymmetrical. My mother is a parent of me, but I'm obviously not the parent of her. So it's not symmetrical. It's asymmetrical. So for all x, for all y, if x is a parent of y, then it is not the case, we have a denial, that y is a parent of x. It's asymmetrical. There's also something known as anti-symmetrical, which is different and very confusing because the terminology in the standard textbook is not ideal. And we'll get into that in a few minutes. But we have symmetrical relations, and then we have asymmetrical relations. And then later we'll get into what's called anti-symmetrical relations, which are not the same thing. Now, when it comes to transitive relationships, we're thinking about three things. A transitive relationship tells us if one thing is related to a second thing, and that second thing is related to the third thing, then that first thing is likewise related to that third thing in the same manner. For example, consider the example of ancestor of. That's transitive because, for example, if a grandparent is an ancestor of a parent and a parent is an ancestor of a child, then that grandparent is an ancestor of that child. Or consider the example taller than. That's transitive because if Tom is taller than Bob and Bob is taller than Stephen, it then follows that Tom is taller than Stephen. And we could symbolize taller than. So here, note that we have three quantified variables because we're thinking about three different people or three different things. For all x, for all y, for all z, if x is taller than y, and, where that symbolizes and y is taller than z, then x is taller than z. In contrast, let's think about something that's intransitive. For example, mother of is intransitive. If Mary is the mother of Susie, and Susie is the mother of Tom, it doesn't follow that Mary is the mother of Tom. So let's symbolize that into the language of predicate logic. So we have three quantified variables for all x, for all y, for all z. If x is the mother of y and y is the mother of z, then it is not the case that x is the mother of z. Now, when it comes to diagrammatically representing transitivity, we can do it in this manner. So we're thinking about x related to y related to z, where we can draw an arrow from x to z. So we have this arrow from x to z in this transitive relation. Now, what about equivalency? Well, equivalency actually combines the reflexive principle with the symmetric principle and the transitive principle. So, when it comes to equivalency, we can say that it is reflexive plus symmetric plus transitive. Think of mathematical equality, or let's say mathematical congruence. So if A is congruent with B and B is congruent with C, it follows that A is congruent with C. Now, when we're thinking about this mathematical congruence, note that first it is reflexive because every shape is congruent with itself. Moreover, if shape A can be perfectly moved to match shape B, then shape B can be moved to perfectly match shape A. Hence, it's symmetric. Finally, if A is congruent with B and B is congruent with C, then A is congruent with C, so it's transitive. So equivalency combines those three types of relations. Now we can think of a relation as a set. Consider two sets. So here is one set filled with objects. Let's call this set A, and it's filled with person 1, person 2, and person 3. And let's say we have set B, and it's filled or contains person 4, person 5, and person 6. Both sets are filled with objects, and we can relate particular members of one set with particular members of another set. And that relation formed can be thought of in terms of a set itself. So let's say person 1 is related to person 5. Person 2 is likewise related to person 5. And person 3 is related to person 4. In this case, person 6 is not related to anyone in set A. But we have this relation, R. And we can think of R as the set person 1, which corresponds to person 5, person 2 corresponding in this relationship with person 5, and person 3 is in a relationship with person 4. So relation R between set A and set B is a subset of A cross B. So A cross B. That is, we have ordered pairs. Here's an ordered pair. Here's an ordered pair. And here's an ordered pair. Those are our relationships. So we can say that lowercase a, lowercase b is a member or element of A cross B. Similarly, we can have a relation R on set A as a subset R subset A cross A. So we might have something like this, where set A contains the elements or members, let's say 1, 2, 3, and 4, where the relation R, we have the ordered pairs 1, 1, 2, 3, and 3, 2. And we can draw that out. So let's say we have, here's 1, here's 2, here's 3, here's 4. Let's notice that 1, 1 is in a relation. That's reflexive. So we can draw or illustrate what's going on that way. 1 loops to itself, so to speak. We have the relationship 2, 3. So 2 goes to 3, but also we have 3 going to 2 in a relationship. So it loops back. We can also think of inverses. You have inverse relations. So consider R being the relationship older than. But that relation has an inverse. We'll say R to the negative 1 would be younger than. Or in other words, we can say it's equal to lowercase a comma b such that lowercase b comma a, which is a member or element of R. We have an inverse. Note that when it comes to symmetric relations, a symmetric relation has its own inverse. So consider if x is married to y, then y is married to x. Well, the inverse would just be if y is married to x, then x is married to y. Now, previously I mentioned anti-symmetric relations. What are those? Well, the thing here to note is that anti-symmetric is not the same thing as not symmetric. So this is not the same thing as not symmetric. I wish the terminology was different here. Really, what it's saying is this. For all x, for all y, that xy is an element or member of R, the relationship, and y comma x is also a member of R, the relationship. If that is the case, then x is equal to y. Notice that in a symmetric relationship, it is mutual and then it goes both ways. Remember, we're going from x to y in this loop. However, in an anti-symmetric relationship, we can only go both ways when they are the same element. That is, when x is equal to y. Consider the relationship at least as tall as. Well, if we think about this relationship, R, first off, it's reflective. Why? Because everyone is at least as tall as themselves. But it's not symmetric. Because if Plato is at least as tall as Aristotle, it doesn't necessarily mean that Aristotle is at least as tall as Plato. However, it's anti-symmetric because if Plato is at least as tall as Aristotle and Aristotle is at least as tall as Plato, then they must have the same height here, because then x would equal y. So other anti-symmetric relations include greater than or equal to. Another one would be less than or equal to. But here's something potentially confusing as well. Not only the terminology, what about something like less than? We will actually consider that anti-symmetric. Why is that? Well, it's only vacuously true. So if we have if x is less than y and y is less than x, then x is equal to y. But if we have this antecedent as false, then whatever the truth or otherwise of that consequent, it is just defined to be a true conditional. So notice that the definition of an anti-symmetric relationship is this conditional. So if this antecedent happens to be false, you just have something that's anti-symmetric. So even less than is anti-symmetric. So this allows us to think about mathematical relations. So let's consider relations on the real numbers. We have things like less than, we have things like less than or equal to, we have equal to, and we have not equal to. So we're just going to think about these different possibilities. What's reflective? Reflexive, excuse me. What is symmetric? What is anti-symmetric? What is transitive? And what is equivalent? So first off, in terms of what is reflexive, well, certainly equality is reflexive, but also or equal to is reflexive. What about symmetry? Well, clearly equality And that inequality is symmetric. If 4 is not equal to 2, 2 is not equal to 4. What about the anti-symmetry? Less than is going to work. We talked about that. Less than or equal to will work, and equal to will work. What about transitive? Less than is transitive. Less than or equal to is transitive, and equal to is transitive. What is equivalent? Well, it's going to be what is equal to. Of course, notice that when it comes to equality, that's equivalent because it is reflexive, symmetric, and transitive. Relations in mathematics are naturally very important. We have the equal to symbol for equality, and we use it often. Mathematicians have thought about relations in great detail. Set theory, one might say, is at the core of pure mathematics for sure. That's why relations are thought about with sets. However, relations are not confined to mathematics per se. We have non-mathematical relations all around us. Still, we can utilize set theory to help us think about the logic of those relations regardless. Many examples of social relations have been used in this video: parent of, mother of, etc., etc. Propositions with these relational predicates have been translated into the symbolic language of predicate logic. Consider learning predicate logic if you don't know it already. Logic is more than just arguments. It's also more than just so-called categorical propositions. We have, for example, so-called superlative propositions, and down below I have a link to a video on that very topic. Anyhow, I hope this video was helpful to you in some way. Please consider giving this video a like, thank you, and if you haven't already, subscribe to this YouTube channel. Be well.